welcome to the Facility for Rare Isotope Beams, or FRIB as we like to call it. My name is Beanley, and this Saturday morning physics talk is part of an initiative at FRIB called the Advanced Studies Gateway. The purpose of the Advanced Studies Gateway is to inspire people. We bring together researchers, innovators, creative thinkers, artists, and performers from all different fields, and build ties between Michigan State University and the community. This talk today, we are very happy to have Professor Gregory Severin, who will talk about so many elements, so little time. Professor Severin is an expert on radionuclides and their applications as tracers for biological, chemical, and physical processes. Professor Severin grew up right here in Okemos, Michigan. He was drawn to nuclear science after touring the National Superconducting Cyclotron Laboratory as a teenager. He received a master's in chemistry in 2006 and a PhD in experimental nuclear physics in 2010, both from the University of Wisconsin-Madison. After that, he was a researcher and then a senior researcher at the Technical University of Denmark. And in 2016, he joined the National Superconducting Cyclotron Laboratory and the Department of Chemistry at MSU as an assistant professor. Before beginning the program, however, I need to take care of a few administrative items. In the unlikely event of an emergency or an alarm, please exit the building through the doors through which you came. I also should mention, if you haven't done so already, to silence your phones. And the last item I want to mention is that if you would like more information about the Advanced Studies Gateway, you can go online to frib.msu.edu/gateway. And now, at this time, it's my great pleasure to introduce Professor Gregory Severin.
Thanks, Dean. I'm really happy that there's a manageable crowd. You guys. Actually, but it is actually really nice. But it is a kind of a small crowd, so I feel like it's a bit like. Feel free to ask questions. Feel free to interrupt me. There'll be plenty of times when many people will catch me telling things which are slightly not true. But that's because those people will catch it because they know too much. Okay, so anyway, I wanted to just talk about what is exciting to me about nuclear science. And I was putting the talk together, and everything I was finding was leading me back, like pointing to this particular nursery rhyme about St. Ives, and I can still see that, and it's loosely connected to what I'm talking about, but mostly just because the number 7 kept popping up. Okay, so the main point that I want to make with this talk, and well, at least the first part of the main point of this talk, is to point out that the universe is enormous, but by and large, it's made of just 3 small things, and this is my first of many lies to you. It's made up of way more than just 3 small things, but for the interest of most things we deal with in our lives, it's 3 small things. Okay, so just to point out how incredibly large the universe is, there are 7 times 10 to the 22nd stars in the observable universe. So that number is drawn out here. It's a really big number, so 7 with 22 zeros after it. And this is by observations from the Hubble telescope, amongst other things. So here's our first 7, but one thing which was really interesting, and I'll plug the planetarium real quick, is that researchers have been finding planets around stars, and recently, so in 2012, there was a Nature paper which came out which stated that there are 1 or more bound planets per Milky Way star, and that to me is quite amazing. So if you think of 7 times 10 to the 22nd stars, and each one of those has at least 1 planet. For the sake of the poem, let's just say it's 7 planets. Okay, so then here's a comment from that paper. They say, we conclude that stars are orbited by planets as a rule rather than the exception. So there are so many planets out there, and the reason I'm really pointing this out is because you can go to the planetarium tonight at 8 o'clock, and you can see a planetarium show about how these planets are found. Okay, so that's just across the street. I'm sure everybody in here knows about the planetarium. Okay, so if you were to zoom in on each one of, or on one of those planets, let's say you picked just a random planet, like Earth, and you looked at all of the air, which is, for example, in the atmosphere of that planet, or in whatever other planet, maybe it's not air as we know it, but let's just say it has an atmosphere like Earth, and you assume that the creatures that live there have lungs about the same size as humans do, then in that atmosphere, there are 7 times 10 to the 20 lungfuls of air there. So this is also an incredibly large number. So this is just one of 7 times 10 to the 22 or more planets in the universe where there are 7 times 10 to the 20 breaths of air. Okay, if you look inside of those breaths of air, and it's lost. Yep. All right. Anyway, if you look inside those breaths of air, you can find that the breaths of air are made of molecules. And in this case, this is just a silly cartoon where you could imagine that the red ones are oxygen molecules and the blue ones are nitrogen molecules. So in each breath of air, there are 7 times 10 to the 19 molecules. Okay, if you look at those molecules, by and large, they are nitrogen molecules, each which is made of 2 nitrogen atoms. And every nitrogen molecule has, every nitrogen atom has 7 electrons around it. Okay. And then if you were to look inside, look deeper, you can see that each of these has a nucleus. And if you were to look at those more closely, you would see that they had 7 protons and 7 neutrons. Okay, so I'll just slow down here a second and just say the 3 things which the whole universe is made out of are these protons, neutrons, and electrons. You could go deeper and deeper and deeper and find smaller and smaller things, and for the point of how we interact with the world, it doesn't really get much more interesting, in my opinion, than protons, neutrons, and electrons. Okay, so as I was at FRIB on Saturday, the universe had 76 trillion stars. Every star had 7 planets. Every planet, 700 quintillion breaths. Every breath, 7 quintillion atoms. Every atom, 7 protons, 7 neutrons, and 7 electrons. So, electrons, neutrons, protons, atoms, breaths, planets, stars. How many were at FRIB on Saturday? I don't know. This is going to the point of this nursery rhyme, which is, there is no point to it, because it's absolutely ambiguous. And to the point of this, it's almost absolutely impossible to fathom these numbers. So if you were to add up all of the protons in all of the breaths in all of the universe, you would get 10 to the 65 protons. If you added up all the protons that are just in the universe, you get something like 10 to the 80 protons. So that's 1 with 80 zeros after it. So this is to say, the universe is incredibly large, and it's made of just 3 small things. Okay, the reason that this is interesting is because the way that those things arrange themselves, so the protons and the neutrons and the electrons, determines how everything in the universe is actually, things are different from each other. So we could see that Earth has got a lot of different features on it. All of those stars look very different than Earth. There's so much variety in the world and in the universe, and it's all related to how the protons, the neutrons, and the electrons arrange themselves. So we already looked at nitrogen, which is 7 protons and 7 neutrons. Okay, if I added an extra proton and an extra neutron, then all of a sudden I have oxygen. So that's 8 protons and 8 neutrons. And I guess most people probably are familiar with that oxygen and nitrogen are not the same thing. So one of them, nitrogen, it bounces around and it's inert, almost useless to us in our day-to-day lives, except that it helps fill our lungs. But oxygen is what we need to survive. So just by changing the number of protons and neutrons and electrons, then we go from something which is not very useful to something which is very useful to life. Okay. So if you go back to the nitrogen again, and if you remove a proton and a neutron, then you get to carbon. 6 protons and 6 neutrons. And now this is something which is very different than nitrogen as well. This is one of the things which is the backbone of our entire, of all biology. Okay, so if you were to look at this nitrogen molecule, and you were able to do some magic, which is absolutely impossible to do, but let's just imagine you could do it, and you could pull a proton and a neutron from one of the nitrogen nuclei and move it over to the other nitrogen nucleus, then you would go from something which was dinitrogen, which is absolutely inert and doesn't really do much, to now carbon monoxide, which would kill you in the flash. Okay, so you can see that there's the way that these protons and neutrons arrange themselves leads to huge variety in the universe, and that's what leads to all the heterogeneity in the universe that we can observe. Okay, so all matter is just different combinations of protons, neutrons, and electrons. And just to point out about you yourself, if you weigh 154 pounds, which I don't know how many people in the room weigh that much, but if you did, you are made of 85 pounds of protons and 69 pounds of neutrons. And a very little bit of electrons. Okay, so this is just to give an idea, and really to, I guess, I don't mean to be rude, but we're all just walking bags of protons and neutrons. Okay, so that's what you're made of, that's what everything's made of, is protons and neutrons and electrons. Okay, the simplest combinations of protons and neutrons are the chemical elements, and those are arranged on the periodic table. Okay, and these are ordered by number of protons, and they're grouped by number of electrons, number of outer electrons. Okay, so we've got this periodic table, and you can look in all the numbers on top of all the element symbols are designating what the proton number is, and the way that this periodic table is structured is governed by the behavior of the outer electrons. Okay, so we can look and we can organize the universe that we observe by proton number and the behavior of the electrons. And so one thing that's important to ask is, what about neutrons, and what role do those have in this? And this is just basically the one way to think of it is, if there are too many or too few neutrons in a nucleus, that nucleus will be unstable. And by unstable, I mean radioactive. Okay, so if you were to look at any given element, so for example, oxygen, there are multiple versions of oxygen with different numbers of neutrons. Some of them are stable, some of them are unstable. So you can look, the oxygen that we're familiar with is 8 protons, 8 neutrons, that's oxygen 16. That combination, that can last essentially forever, unless it's hit by energetic particles. The same with oxygen 17, so if you add a neutron to oxygen 16, that's also stable. If you add another neutron, oxygen 18, it's also stable. But if you add one more neutron, then you get oxygen 19. And these 8 protons and these 8 neutrons, they don't get along, or they don't stay that way forever. And what will happen in order to reset the balance is one of these neutrons will essentially turn into a proton and an electron. Okay? On the other side, if you go to too few neutrons, you can get back to oxygen 15, and oxygen 15 has 8 protons and 8 neutrons. And what happens in order to restore a balance is one of those protons will turn into a neutron and an anti-electron. That anti-electron will find an electron and annihilate, so you can think of it overall as a proton absorbing an electron and becoming a neutron. Okay, so this is how radioactive decay works for the most part of the elements that we deal with on a day-to-day basis. For the most part, none of them are radioactive. But you can see that there are many combinations of protons and neutrons which are radioactive. And this one of them, yeah?
Could you explain the beta and the epsilon underneath the elements?
Yeah. So the beta minus, so the decay that I was talking about where you take a neutron and you turn it into a proton and an electron, that's called a beta decay. And we call it beta minus decay because what you observe is the emission of an electron, which is negative. And that's the beta particle, is an electron. So the proton, or the neutron becomes a proton, and you see an electron come out. On the other side, these epsilons, these mean electron capture. Okay, and electron capture is the opposite process. You take an electron, you add it to a proton, and you make a neutron. The way that this is the way that we call it. We say electron capture because you can imagine. There are two ways in which this can happen. Either the nucleus can emit an anti-electron, which is called a positron, and that basically is antimatter, and it runs into an electron and they annihilate each other. Or the nucleus can actually just absorb an electron directly. So sometimes with the ones on the left-hand side of the chart, things which have too many protons, we can see electrons being captured, and sometimes we can see antimatter being emitted. Okay, so one thing to note about these different isotopes is that each one has a different lifetime. So depending upon the arrangement of the protons and neutrons, then you can ultimately end up with things which have short half-lives or long half-lives. So the other thing that's interesting about them is that they all emit different radiation. Okay, you can emit all of these on the right-hand side will emit the electrons, but they'll come out with different energies and be associated with extra gamma rays. Sorry, Mom. I'm going to get to this one next. So, okay. Yep. Okay. So there are some elements which have only radioactive isotopes. So there is no combination of anything with 92 protons. So no nucleus with 92 protons, which will last forever. So this, for example, is uranium. This is a picture of uranium metal. And that is made almost entirely of uranium-238. So that's down here. It's the natural abundance. Sorry, it's hard to see. It's 99.27%. That decays with a half-life of 4.5 billion years. Okay, so which is to say, this piece of metal will have decayed. Half of it will be gone in 4.5 billion years. And then to put that in perspective, the age of the Earth is 4.5 billion years. So since the beginning of the Earth as we know it, half of the uranium has decayed. Okay, so we can still go out into the world and we can find uranium. Yeah.
You know why it's like also there's like SF, I believe that stands for spontaneous fission. Do you know that why those are such low percentages?
Yeah, so these combinations are actually reasonably stable. Okay, and there can be, I guess, so this is something that probably goes much better to deep, but there could be fluctuations within so there's a statistical probability that the nucleus can find itself in an arrangement where it can actually fission on its own.
So, spontaneous fission is pretty rare. I believe there's this really cool type of decay called cluster decay, I believe, that happens with protractinium, I believe 223.
Okay. So you surpassed me in knowledge and fancy decays. I thought I knew them all, but I don't know cluster decay. But maybe others do. There are some interesting decays where you can have emission of a carbon-14 nucleus. I don't know if that's... but anyway, you can see down here, actually, this is kind of interesting. You can have uranium-233, which can emit neon-24 with some extremely low probability. Okay, so, but just to point out, okay, this is uranium-238. If you alter the number of neutrons in this, then you get something which is very different. Okay, you can get, if you take out 3 neutrons, you can have uranium-235. Okay, and if you had 7 grams of uranium-235, you can get as much energy out of that as you can get from 1 ton of coal. And then to put that in perspective, this is probably, it's at least 1,000 grams of uranium metal And so if that were all uranium-235, you would be able to extract an enormous amount of energy out of it. Okay. So what's special about radiation? In my point of view, it's special because on the previous slide, it carries a lot of energy. It's debatable whether that's what we should do with our society and how we should fuel what we do. But it's interesting nonetheless, and it's special that it carries a lot of energy. But the other thing which is really special about it, which is much more to do with what I'm interested in, is that you can detect it. Okay, we can detect it with different kinds of, with many different ways. What I wanted to point out here, this is a picture of gallium-66, which is a 9-hour half-life. It emits positrons, and it's sitting in isopropyl ether on top of hydrochloric acid. And this is a photograph that I took inside of a black box, just capturing the natural light which was coming from the beta particle slowing down in the isopropyl ether, or sorry, the positron, beta plus. And so you can actually see the light which is coming from radioactive decay, or as a consequence of radioactive decay, but we can also detect it with extremely high sensitivity. Okay, so this, and I think from now on in the talk, I just want to go through some examples of different arrangements of protons and neutrons, which can give you different applied results. Okay, so this is a picture of George Hevesy. He did a lot of wonderful things. He won the Nobel Prize. He discovered the element hafnium. But one of the first things that he's famous for was solving an apparent crime using lead-212. Lead-212 has 82 protons and 120 neutrons. And I probably didn't add that together. It's 130 neutrons. So sorry. It's an 11-hour half-life, and it emits a beta minus. Okay. So there was a question in George Hevesy's dorm when he was at Manchester. There was a question about whether the landlady was taking their half-eaten meat and then recycling it, putting it into the next day's soup. Okay? And this was like, so people were convinced that this was probably happening, but they had no proof. And so this is the first example of someone using radioactivity, in my knowledge, to solve a problem like this. So what Hevesy did was he took some radioactive chloride and he sprinkled it onto his sandwich and left his sandwich for the landlady to take back. And then he came back the next day and he took his radiation detector up to the soup and found out that it was radioactive. So this is solving crimes with lead-212. I think this was around 1920-ish, 1910 to 1920 when Hevesy was in Manchester. Okay. So that's, the first example of radio tracing, which I think is just fantastic, and it really gives you the idea of what you can do with radioactivity. You can attach something radioactive to something you want to study. You can let it undergo some process, and then you can observe what it ends up as. Okay. Hevesy did a lot of other wonderful things, and he got the Nobel Prize. He didn't get the Nobel Prize for specifically catching the landlady, but he did get it for his work on the use of isotopes as tracers in the study of chemical processes. Okay, so you can make observations about radioactive atoms, and the one observation is that chemically they behave the same as non-radioactive atoms. Okay. So, for example, radioactive carbon and non-radioactive carbon both react with oxygen to form carbon dioxide. And so you can take radioactive carbon-11, for example, you can make it in a cyclotron, you can react it with oxygen, and now you can have radioactive carbon dioxide. If you make a nice atmospheric box and you pump this radioactive carbon dioxide into this box and you put a plant inside, the plant will start doing photosynthesis. It will absorb this radioactive carbon dioxide, and then you can observe in the plant sort of what's the photosynthetic process going on. Okay, you can see with radiation detectors where this radioactivity is going. So you can actually observe the uptake of carbon dioxide into plants almost in real time. This is an interesting one because it's carbon-11. It has 6 protons and 5 neutrons, and it has a half-life of 20 minutes. So this isn't the first example of what you can do with radioactive carbon in plants. There was an earlier study which was done with radioactive carbon-14, which has got an over 5,000-year half-life. Same idea. You introduce radioactive carbon into plants, and then you let them go through their photosynthetic path, and you can observe at every single step along the way what becomes radioactive and what doesn't become radioactive. And then that way you can trace the carbon that you put in initially as carbon dioxide up here. You can trace it through an entire chemical synthesis pathway leading and figure out what is photosynthesis. So this was done by Melvin Calvin in, I don't know when he did it, but he got the Nobel Prize in 1961 for using radioactive carbon, carbon-14, to figure out what really is happening in photosynthesis. Okay. There are other cool things you can do. You can make radioactive water using radioactive oxygen. So radioactive oxygen 15, it has 8 protons and 7 neutrons, and has a half-life of 2 minutes. So this very short half-life, if you can very quickly make it into water, and then you can inject it into a person, you can look at where water flows in that person. Okay, so there was a study which was done, published in 1999, of injecting into a person radioactive water, and then looking at where does blood flow in the brain as a result of different stimuli. Okay, so what they could find was that when a person was hearing words, a certain part of their brain would get more blood flow directed to it. Okay, when they were reading and seeing words, then a different part of the brain was activated. And then if they were speaking, even a different part of the brain was getting excess blood flow. And ultimately, if they were just thinking about words, that was another part of the brain. Okay, so what you can do with just a simple molecule, once you make it radioactive, is you can start to understand things not only about how the plants behave, but you can start to understand how does the brain work, and other physiologically interesting questions can be answered. Okay, this is one of my favorite studies, mostly because it was done by my postdoctoral mentor, Jerry Nichols, who was a bit of a radiation cowboy. This is a hand drawing that he published of himself sitting near the accelerator. What he was interested in doing was seeing how long does it take for oxygen to get from your lungs down to your feet and back. So he wanted to know what's the oxygen circulation time. And so what he did was he took a deuteron beam, irradiated, so that's a proton and a neutron together, it's a deuteron, took a deuteron beam and irradiated oxygen and nitrogen at the same time to make 2 isotopes of oxygen, oxygen 15 and oxygen 19. And these have got different half-lives, one half a minute, the other 2 minutes. And what you can do then is you can say, well, I know how much oxygen 15 and oxygen 19 I have at one point in time if you measure it, so that would be over here at this detector here. You can push everything into this detector, so radioactive oxygen to here. You can say how much is in there, and you can push that over. The professor can breathe it in. And then you can look and say, all right, what's the ratio of these 2 isotopes in the lungs? And then ask again with another detector, what's the ratio of those 2 isotopes in feet? And what they were able to do was determine that it takes about a minute for the blood, or for the oxygen in your lungs to get down to your feet. Okay, so it's fun to think that people used to be able to just hook themselves up directly to the cyclotron. We don't do that anymore. And I would say, it is for a good reason, but it's kind of fun to dream about these kinds of experiments. Very, very simple experiments where you're just breathing in some oxygen and you can then learn something which is kind of interesting about your physiology. Okay. One of the most important uses of radioactivity now is with fluorine-18, which is 9 protons and 9 neutrons. It has a 2-hour half-life. You can take glucose and you can exchange of fluorine for one of the hydroxyl groups. And you can have that be radioactive fluorine, so fluorine 18 on glucose, so this is sugar molecule. And now replace one of the hydroxyl groups with the fluorine, you have something called FDG, this is fluorodeoxyglucose. Okay, but essentially it's just radioactive sugar. Okay, you can inject that into a person. Okay, and you can see where in their body is sugar metabolism going on. Okay, and so this is an image of a person, essentially a healthy person. And what you see is where it's a heat map. So where's red, the things that are red and yellow and white are high uptake, high metabolism, and places which are darker are lower metabolism. And what you can see in this person is you can see that the organs in the abdomen, they do some sugar metabolism, but really you get a lot of activity in the brain. So your brain is constantly using a lot of sugar. Okay, the reason that this is such a valuable thing to look at is not because of the use of sugar in the brain, that is interesting in itself, but because you can do the same thing with cancer patients. And this is actually an image of someone who's in remission from non-Hodgkin's lymphoma treatment, and a picture of them after they've had chemotherapy. And this is the same person before they had chemotherapy. And so you can see in this patient extensive disease. So what you're seeing there is the lymphoma before they've had their chemotherapy. Okay, and so after delivery of the chemotherapy, then a doctor can take another scan with this radioactive sugar, and they can say, was that therapy effective or was it not? So this is very, very valuable, and it's become a huge market in the U.S. for helping people in terms of cancer treatment, cancer assessment, and things like that. So this is actually a very, very valuable technique. I think there are more than 1 million scans in the U.S. every year done with this. Okay, so that's not the end of what you can do in the sort of cancer fighting domain. These are very, very similar images. So what you can do is you can take radioactive gallium-68, which is 31 protons, 37 neutrons. It has a 1-hour half-life. And you can attach it to a molecule which is it's called PSMA, which is not to be confused with the real PSMA. It's actually a small molecule which can bind selectively to the prostate-specific membrane antigen. So in patients who have metastatic prostate cancer, you can use this gallium-68 with this PSMA ligand and inject it into them, and you can see where in their body do they have this metastatic disease. Okay, so you can see some of these patients. There are 8 patients total. Okay, and on the left-hand side, you can see the preliminary gallium-68 scan. All right, you can see this metastatic prostate cancer, extensive. That's the red images. Okay, and then you can take that same tracer and you can replace the gallium with lutetium, which has 71 protons and 106 neutrons and a 7-day half-life, so lutetium-177. And that lutetium will emit beta radiation at those same locations that you've identified with the gallium and eradicate the cancer. And so this was the 2018 Image of the Year for the Journal of Nuclear Medicine, which was essentially showing patients on the left before they've had any treatment. This is how their gallium scan looks, so where's the cancer? And then on the right, they've had a lutetium-177 treatment course, and you can see that it's another gallium scan, and the disease in this case has been eliminated. Okay, this is fantastic, and this is really pushing. It's pushing that we do a lot more research into how to find more of these tracers, which can find metastatic disease, and how to use different radioisotopes to help cure cancer. It doesn't work well for everyone, but in the cases where it doesn't work, then there's another radioactive answer, which is actinium-225. So this is 89 protons and 136 neutrons. It has a 10-day half-life, and it emits a chain of alpha particles. This can do very, very localized damage to cancer. So this is a patient who has already tried to do the previous the previous treatment. So they tried to do the lutetium-177 treatment, and it was not effective. But then they were given actinium-225 with the same tracer, which gives a more localized, higher energy deposition, and they were able to be, I don't know if you can say cured, but they at least were brought into remission. So we can go from, let's see, 71 protons and 106 neutrons to 89 protons and 136 neutrons, and now you go from something which didn't cure cancer in a patient to something which did. Okay, so, yeah.
How do these, I guess, radioactive isotopes target the cancer cells directly?
So what they do is, it's this, the molecule, this is called the PSMA, so you can see the 225AC-PSMA. So PSMA is this, it's, in reality, it's prostate-specific membrane antigen, which is a protein which is overexpressed on prostate cancer cells. There's this ligand which we call PSMA. It's not PSMA, but it's a ligand which will selectively bind to that. So it's a small urea derivative that looks like two back-to-back amino acids. You can bind the actinium to something called a chelator. So this is like it's something like EDTA. I don't know if you're familiar with that, but you could basically put the metal actinium into an organic cage molecule. You can attach it to this thing which looks like a urea, which the PSMA, which selectively sticks to the prostate-specific membrane antigen. You inject that, it circulates around, and that targeting ligand will just accumulate on the PSMA, which then ultimately you get the decays and you get the effect. Okay, so it's not actually these. It's not actually the actinium itself which is doing the targeting, but you can use it as sort of the treatment. Okay. Radioactivity doesn't just protect you from cancer. That's a weird thing to say. But it also helps to protect you in your house. In the smoke detector in your house, there is very likely americium-241. That's 95 protons, 146 neutrons, and it has a 400-year half-life. And what it does is these alpha particles are emitted from americium-241, and they travel from the source to essentially to an electrometer. If you have smoke, which is made with a lot of ash, and these alpha particles have to travel through the ash in the air, they get blocked by the ash, and then you no longer get alpha particles reaching your electrometer. If the alpha particles stop reaching the electrometer, then the smoke alarm will go off. Okay, so in your house, you have radioactive americium protecting you from fire. Okay. Something which is a little bit more lighthearted was something when I was at the Technical University of Denmark. I thought this was just really fun. In Danish houses, they use underfloor heating to help regulate temperature rather than using radiators essentially these are radiators, but underfloor heating, which is just pipes which go under the floor in your house, and you can pump hot water through them and they'll heat up your house. What happens very often is that there will be a small leak somewhere, which only is identified by some essentially damage somewhere remote to that place. So you can have something leaking from your ceiling if you had it on the second floor. So one issue is, there's a leak, you want to know where it is, so that you don't have to rip up your entire floor in order to find out where you have a leak. And so what you do in Denmark, which I don't think we could do here, but you can do it there, you can take some ammonium bromide, you can bring it to a Norwegian reactor, you can have it be made into bromine 82, and then you could inject that into your water pump inside of your house. You let the radioactive bromine go through the house, and then you come by with a radiation detector, and you look for where is there a huge signal of radioactivity, and that's where you have a leak of water coming out of the pipe. Okay? So this is actually, I mean, it's cool. You can do this in Denmark. Yeah, don't think you could do it here, but this is actually the technique that people use in to determine whether or not oil and gas pipelines are still viable. So you can send radio tracers through an oil pipeline, and if you can observe, you can go by later and observe the accumulations of radioactivity and use that to determine whether or not those pipes have been leaking. Okay, other cool things that you can do. Technetium-99 ground state. So technetium is something which is not naturally found on Earth. It's element number 43, but it's made in nuclear reactors from the fission process. It has this particular isotope has a 200,000-year half-life. And what happens when it's used in reactors, there are some places in the world, there's a place called Sellafield, which is in Great Britain, where reactor fuel is reprocessed. And when the reactor fuel is reprocessed, then this technetium is taken out of nuclear reactor fuel. It has essentially no really discernible radiation. So what ends up happening is it ends up getting put into the ocean. This might sound unpleasant, but it really is does not emit very much radiation. And what's cool about it is technetium is not normally present on the Earth. So you can now go and take water samples, and you can observe at different places what's the concentration of technetium in the water. And if you know something about how long ago the Sellafield reprocessing plant was working, then you can say, all right, I know they put some technetium in the water 3 years ago. Now I measure over years the technetium in the water. I can determine how long did it take for water to get from Sellafield around to the North Sea. Okay. And what's interesting about that is that then you can start to map ocean currents, and you can actually get really nice data about how do the ocean currents move and how long does it take for water to get from one place to another. And a lot of the data that people use now to understand how ocean currents are changing due to global warming and things like that is based upon the distribution of technetium-99 in the oceans. Okay. I think this might be my last example. Iron-60, it's 26 protons, 34 neutrons. It has a half-life of 2.5 million years. What that one is used for, with a 2.5 million year half-life, it's decaying half of its gone in 2.5 million years. In a stellar explosion, so in a supernova, you can expect that you make all types of isotopes, and the ratio between the different isotopes of iron has sort of a fingerprint to it. Depending on how much of this iron-60 is made relative to the others, and then how much you observe relative to other iron isotopes, then you can determine how long ago did a supernova happen. Okay, and the way that we make these people make these observations is there are satellites which are constantly collecting space dust and constantly then measuring the isotopic ratios between iron-60 and the other isotopes of iron. And what you can then do is use that as a clock to tell you how long ago did the supernova occur. Okay, and then based upon the speed at which this space dust can travel, then you can determine how far away was that event. Okay, so this is kind of to get back to the beginning and this idea of so many elements, so little time. I was able to show examples of radio tracers used with all of these different elements. There are so many more, and every single element has got radioactive versions of it. So you can just go on forever and ever with what you can do with all of these different radio tracers, or possible radio tracers. And then I wanted to finish with something which is a friend of mine, Professor John Engel, in the medical physics department at University of Wisconsin-Madison. This idea of so many elements, so little time, I think for radiochemists maybe it fits in with the idea that some people have that they would like to go visit every single U.S. state, for example, before they die. Okay, and so John thought that this was interesting. He sort of had all of his life thought that he wanted to go visit all the U.S. states, and since becoming a radiochemist, then he also set another goal So what he thought was interesting was there's an overlap between the U.S. states and the chemical elements, so neon in Nebraska, Alabama, aluminum, et cetera, and he could go through and he could say, okay, these are all the states that he's been to. Okay. And that looks like he's gotten actually pretty far along. And then he could do the same thing since he's been working in radiochemistry and look at all the different elements that he has been able to use in the lab, make radioactive versions of, and really explore the chemistry with. And I think he's getting pretty close to getting everything you could ever imagine doing. And I think that that's pretty cool. And that's, to me, is one of the most exciting things about getting to do radiochemistry and applied radiochemistry is that we get to use so many different elements. We get to study the chemistry of just about anything you could ever want to study. The wonderful thing about FRIB here is that besides all of these, the heavy things, FRIB will make just about every single isotope of every single one of these elements that possible. So in terms of what we could do here in the future as FRIB comes online, we're going to be able to do radio tracing of an enormous number of things. So, just want to say thanks. There's a picture of my group. There are some people that are missing because they weren't there that day, but we do a lot of fun radiochemistry research here at MSU, and pretty soon we're going to be getting into all types of fun radioactive elements. So, thanks.
Very much for a very entertaining and enlightening talk. There must be more questions.
What about Grandma's jar?
Yeah, okay. So I didn't want to break it. Grandma's jar is, I didn't get to put it in, but I was searching through about uranium, and there was somebody's quote that said, somebody was quoting, or like a website saying, there is no other use for uranium than nuclear energy. And I thought, well, that's not true, because my mom has a jar that we could put hard candy in, and it's made out of uranium glass. So, I thought that I could point out that there are other uses of uranium than energy. And then the really cool thing about it is that if you shine UV light on it, you can get fluorescence in uranium. Maybe we'll see it. You can shine UV light on it and it will glow. And it's not glowing due to the radiation, but just glowing due to the chemistry of uranium. So I thought this is pretty cool. I don't know if everyone can see it, but when it wasn't on the light, it's just normal little depression glass. When you put it on the light, it glows. So that's that. So we had a measurement. There's a Geiger counter here. The measurements showed that sitting in the seat, the background radiation is about, 10, 20 counts per minute?
10, 20 counts per minute, otherwise about 0.1 megaseconds per hour.
Okay. And then when you stuck it inside of the jar?
80 counts per minute, I believe the 0.5 megaseconds per hour.
Cool. So that if you put your hard candy inside of this jar, it'll get very, very slightly irradiated. Okay, other questions?
What kind of research do you do specifically in your lab?
Yeah, okay, so what we are interested in is that our whole purpose is to take these interesting isotopes which are made by FRIB and get them into applications like the ones that I showed. So what FRIB will do is take heavy ion beams, so wonderful physicists do wonderful things looking at the nuclear reactions and the resulting nuclear products, and they're very interested in all of the very short-lived things because they want to understand how do nuclei come together and why do nuclei come together and how do they decay. From the point of view of the applied science, what's interesting for us is this beam of particles ultimately has to stop. And the plan right now is that it stops in water. When it stops in water, the nuclei break to all possible bits of protons and neutrons, and then we can then come along and pump the water out, clean it out, and we can collect all of these interesting radioactive things. Then we can do chemical separations to pull each individual element apart from the other ones, and now we have a radio tracer for almost any element. And so right now, our research, so my research group actually is sitting right up there. Right now, what we're interested in is how can we set up, basically it's a lot of engineering, how can we set up a system to pull these radioactive things out of the water. And then in the future, hopefully very, very soon, we're going to be able to start putting these into medically relevant tracers.
Are there other questions? If not, let's thank Professor Severin once again.